Hi, this is Mrs. McTaggart. In this video, we are looking at recurrence relations and we're looking at the long-term effect of one of the sequences, and namely this is sometimes called limits. I always like to start with this little love story about Mr. Frog. Mr. Frog wants to get across the river, jumping across the lily pads. My blue river's disappeared, but I'm sure you understand what I'm trying to say, to get to his soulmate. But every single time he hops, he only halves his distance. So his first jump would be 5 and he'd get halfway. So his first jump, where's my pen not working? So his first jump would be 5 and he'd only get halfway. Then he'd go 2.5. Then he'd go 1.25. Then he'd go 0.625. Would he ever reach her if she's 10 miles away? The answer is no. Have you ever folded a sheet of paper and just kept halving it and halving it and halving it and halving it? Eventually, you have to stop. Mr. Frog will never make it to his soulmate. If you keep halving and halving and halving and halving, you will never get to the 10 metres, I'm afraid. We'll get super close, but not quite there. We'll get to 9.999. Let's show you this in action with a recurrence relation. So some recurrence relations have an end point. They can't go any further. So here is a very basic one. un plus 1 equals 3 un plus 2. So quickly let's work through this, see what happens. So if u0 is 1, u1 would be 3 times 1, add 2, which is 5. u2 would be 3 times 5, add on 2, which would be 17. u3 would be 3 times 17, add on 2, which is 51, add 2, 53. And the next term would be 3 times 53, add on 2, which is 158. Can you see what's happening to this sequence? It just keeps getting bigger and bigger and bigger. So as my n value, so as my nth term gets bigger and bigger and bigger, so does my answer. So what this sequence is called is it's called, let me try, I've got something hidden here. It's called a divergent sequence. It's divergent because as n increases, so does my answer. It just keeps getting bigger and bigger. Now that isn't always the case. Let's look at the second example. This time I've got a 0.2 in front. So if I was to do 0.2, let me get my pen out again. 0.2 times my initial value of 5, add on 2. That gives me 3. If I do the same again, 0.2 times 3, add on 2, gives me 2.6. If I do this one again, I'm using a calculator here for this one for obvious reasons. The third term would be 2.52. And if I do it one more time, you can see where this is going. It gives me 2.504. Now, I've done the wee cheat where I've put it into my calculator where I put in 5 equals and typed in 0.2 answer button plus 2, and I just kept pressing equals and equals and equals, and eventually it keeps going and going and becomes 2.5 with lots of zeros, and then eventually if I keep pressing the equals button it just settles on 2.5. So at some point if I just keep timesing by 0.2 and adding 2, the answer will stop, because 0.2 of 2 would be 0.5, add on the 2 would give me the 2.5, so eventually it stops at an answer. So the last sequence is called divergent, this one is convergent. As my n increases, it actually tends to a limit, so there's a final answer that it won't go below or go above. Now, why did one do it and why did the other not? I don't know if you noticed my numbers. On the first one, it's all based on this number here. It's all based on your a value. On this one, my a value was a decimal, less than 1. On my previous one, it was 3. So if you're timesing by 3, it is getting bigger and bigger and bigger. So if you're timesing by a small number, like less than 1, it will get eventually tend to a limit. And that also works for negative 0.2. Yes, it would go positive, negative, positive, negative, positive, but it would eventually stop again on a number. So there is a wee bit of a note that I would give at this point. So a recurrence relation has a limit if the recurrence factor, a, the bit we call a, lies between -1 and 1. So this is what you're always looking at. If a question asks you to prove whether or not a limit exists, you look at that number first. If it is between 1 and -1, then a limit exists, and that's literally what we write. So if it has a limit, we'd say it's convergent, it converges to a final answer. If there's no limit, it's divergent, it just keeps going off. And then we have this limit formula. Now this isn't the only way to do limits. Your teacher might do a different way with you. My pupils like the limit formula. I will also show you the other way for one example only, which is the way I was taught when I was at school. Sometimes people find it a wee bit easier, particularly if you can't remember the formula. So this limit formula is one you have to memorise. You have to learn it, I'm afraid. It's not on the formula sheet. That's the downside to this one. That will always find you the limit, because you don't always have a calculator to sit pressing equals and find where it eventually stops. So let's look at a question in action. So un plus 1 equals 0.4 un plus 24. Part A, does a limit exist and why? So quite often an exam question will say, prove that a limit exists, or is there a limit to this sequence? And then we have to find the limit as n approaches infinity. So does a limit exist? Well, yes, because that number there is between 1 and minus 1. So you literally write that. You write limit exists since, and do not write, so in my note a second ago I had this written, right? Don't write that. All you have to do is simply change that A to whatever you have as A in your recurrence relation. So my recurrence relation, I have 0.4. So I'm going to put a 0.4 in there instead of A, and that's all you have to do. Then it says find the limit, so we're going to use the limit formula. So L equals B over 1 minus A. So B is the 24 term. B is what is getting added or taken away each time. So that's 24 over 1 take away. Your A term is 0.4, which gives us 24 over 0.6. My layout isn't great on this. Normally I would just keep working down the way and keep the screen, but I want to try and keep it all in one screen. Now this is non-calculator quite a lot, so you need to be good at doing these. What you have to do is just make an equivalent fraction. Try and get rid of the decimal. Sometimes if it was 0.5, you could just double it. But with 0.6, if I times that by 10, I get 6. So if I've times the bottom by 10, I have to do the same to the top. So I get 240. And then 240 divided by 6 is just 40. So the long-term effect is n approaches infinity. Your limit is 40. So I'll keep doing this sum over and over and over, and eventually my answer will always be 40. It won't go any lower. Let's look at a second example. So example 2. Similar, but this time it's a fraction. So we've got a third. Explain why a limit exists. So again, we write limit exists since. And this time I've got a third. So remember, a third is 0.333. It's less than 1. It's between 1 and minus 1. So we write limit exists since 1/3 is between 1 and minus 1. So you just do that with your little inequality symbol. To say that out loud, it is a third is between minus 1 and 1. Remember, Beyonce, arrows to the left, okay? Then we have to find the limit again, just the same as last time, but this time we've got a fraction. So limit is b over 1 minus a, which gives us, b term is minus 6. 1 minus a will be 1 minus 1/3, which gives me negative 6 over 2/3. Now we don't like that. Please remember, dividing by a fraction is the same as flipping it and multiplying. So that is the same as minus 6 times 3 over 2, which is minus 18 over 2, so minus 9. So as n approaches infinity, your limit will go to minus 9. Okay. Now I did say I was going to show you the other method, so I'm just going to very quickly take a new slide and we're going to look at both of these using the other method. You can completely skip this bit to example 3 if you want. So what I've very quickly done here is I'm just going back to example 1. I'm going to show you the other way. So the other way is to change everything to L. So any of your letters, so un plus 1 and un, you make them all the letter L. So into your recurrence relation, we have L equals 0.4 L plus 24. Then you treat it like a little first year equation. You would then have L minus 0.4 L equals 24, which gives you your 0.6 L. And then you would do 24 divided by 0.6. So you end up with that same line that I had before, which obviously was the same as 240 over 6, giving you L was 40. So that's an alternative method. Some people think it's a lot more working, but some people who are good at two-step equations much prefer that. I'm going to do example 2 again, doing it that way. So we're going to change everything in the recurrence relation to L. So L equals 1/3 L take away 6. Then you do L take away 1/3 L, which is 2/3 L, which is what we had in the bottom of the fraction. So 2/3 L equals -6. I think this is why some people like this method. I'm going to cross multiply to get rid of the third. So I would have 2L equals -6 times 3 is -18. Divide by 2, I would get L as -9. So it's two completely different methods for finding the limit. If you can remember the formula, brilliant. If not, this way works as well. The formula is literally what you've got when you've rearranged it, because basically what I ended up doing is I ended up dividing my B term by whatever I got here when I did 1 take away my fraction. So this is where the L equals your B term over 1 take away the fraction comes from. But it's a shortcut if you remember the formula. I do have one final example. This one here. I tell a lie, I've got 2 examples. So this one says, how long does it take to exceed 28? So you just keep plugging in until you get over 28. So U1 would be 3 times 3 add 4. Sorry, take away 4, which is 5. U2 would be 3 times 5, take away 4, which is 11. U3 would be 3 times 11, take away 4, which would be 29. So it took 3 terms. So it took 3 terms. I wrote that the wrong way around. So 3 terms to exceed 28. If this was in a context, that might have taken 3 hours to go over 28, or 3 days, or 3 years, depending on the question. Interesting bit I want to chat about in this one. Does a limit exist? Well, you can see my answers keep getting bigger. You can see that my A value is just 3. So in this case, you write limit doesn't exist or no limit. Look at my writing here. And it's simply because that number was bigger than 1. Because 3 was bigger than 1. That's all you have to write if there is no limit. Or had that been -3, I would have written -3 is less than -1. Just on the other side of the things. But it didn't ask me that one. So that's how to show there's not a limit. I do have one more example. This little bit has appeared once or twice, where they haven't given you an A value. They've told us in this case, obviously my A term is 2k minus 3. And it says, for what range of values of k does a limit exist? So remember we said A had to be between 1 and -1. So in this case, I'm going to replace A with the equation 2k minus 3. Now what we have to do is you just treat this like 2 little equations. So I'm just going to hide this for a second and think, right, how would you have treated that little equation at National 5 or even S1, S2? Well, you would have done 2k is less than, you would have added 3 to there to get 4, and then you would have said k was less than 2. So that's me on the right hand side. I'm just going to do the exact same with the left hand side. I'm going to bring back in this -1. I'm going to add 3 to that as well. -1 add 3 gives me positive 2. 2 divided by 2 gives me 1. So it's just like performing a little equation on both sides. That's cropped up once or twice, so I just wanted to make you aware of it. Since we're talking limits, that was a wee twist on a limit question. Alright, I hope that's helped. Thanks for watching.